My name is Ogunmefun, mechanical, and I'm glad to be here. Yeah, there's no way you can have industrial that you don't have mechanical. We all need to work together. The topic is dual phase steel, quenched in bitumen. We understand that dual phase steel has a very unique characteristics. And the characteristics is that it has both the eye strength, it has strength, and it has ductility. If you can look at those two together, you find out that that is worthy of all engineering materials anywhere in the world. And vis-a-vis, as it regards Gibella, as it goes into the aerospace technology, as it goes into car manufacturing, to automobile, and anything. So the essence of this presentation is to let you know that this dual phase steel, it's a body, it's a family of an high strength, low alloy steel. What they've been doing in the past, maybe I should leave the slide for now. What they've been doing in the past, perhaps, is to concentrate on the microstructure of this dual phase steel. I was privileged to have worked with Mercedes-Benz and Amco in Nigeria, and I was in design and implementation department. And basically, we design the jigs and the fixtures. Basically, we monitor what they do, we design what has to be implemented on the buses. We actually were dealing on the commercial buses. So, but there was something that was so keen, that was so interesting to me at that point in time. I realized that the mild steel that was being used then, it's so thin. Not considering the gauge, because we have several gauges. We have mostly used in the automobile industry. We have the 0.9, we have 1.2 gauge, we have 1.5. I think that should be the highest. So as to limit, check the weight that's going to be imposed on the bus for tractive movement. So as I developed a keen interest when there was a little accident that happened in the production floor. And it was just one of those spot welding that was meant to be used to tack. You understand what I'm saying? For some of us, I'd say that was meant to use to tack the panels, the mild steel. Just got punctured. Then I said, why should it be? I mean, this means that this does not have a crash resistance. So I began to develop interest. I'm trying to know how it can be done. I went into some researches then I realized that there is a dual phase steel. Literature tells us that it belongs to what I can call a ferritic martensitic yard, meaning that it has an element of ferrite and it has an element of martensite inside. We all know the technology of developing a martensitic steel. You heat beyond the critical level, beyond the intercritical annealing temperature, then you suddenly quench. You definitely have a martensite. But then, we now decided that, okay, this is what we're going to do. Then I went into researches and realized that it has been done far back as 4 decades ago. The normal Bessemer process, we all know that in our methodological and materials engineering, and it's been done crudely. So, but at this point, I just decided, okay, we just decided that we're going to develop something that is extraordinary. Okay, let's see. We realized that 2 things are common. Or let me say 3 things are common. These are the parameters which influences the strength, the mechanical properties of any dual phase steel. 3 parameters. Number 1, they need to be heated beyond critical level. What do I mean by that? There's a level called intercritical annealing temperature, which is about what? 735 degrees centigrade. If we take it beyond that, that means you're taking it beyond the austenite. No, I don't want to bother us into the literature and the thesis. But we realize that when we manipulate those factors, we manipulate the intercritical annealing temperature, which is one of the factors to which you can get our ferritic and martensitic nature of the steel. We can manipulate our holding time in the muffled furnace. Of course, we know that if we have to heat up a steel or material, you use it either in a high induction coil, and high induction coil furnaces, or low induction coil muffled furnaces. So you have to heat it up. You have to heat it up to beyond annealing temperature. You have to do the holding time. You have to consider it. That's one of the factors that gives you the best of the mechanical properties. And again, the last one, which is our quenching medium. Yes, a lot have been done. Water is the most viable, is the most used. If you check all the literature as far back as 30, 40 years, water has always been used. Sometimes cold water. Then we went further, or I went further now, because I'm the one doing it. We went further by using a bitumen, and that's why we're here. Permit me to tell you that the dwarf steel contains some other micro elements, which gives it the best of the quality. Hello? So I'm just talking about the magnesium, the silicon of this world, the aluminum, the cobalt, the chromium, the nickel, and the rest of them. They all have their specific roles they play in advancing, in building up, in encouraging, in improvement in the steel. So we realize that this dwarf steel, we have a high strength to weight ratio. Fantastic. We have a low yield to strength. Very well understood. But in bitumen, we realize that when you put it in a bitumen, after heating to an intercritical annealing temperature, you get something different. As I'm speaking to you, we should be running now because we have done all this, the furnace, the heat treatment, we've done it, we've quenched, we've done everything. But what we are left to do now is characterization. And what do I mean by characterization? Characterization is simple. We just need to know. We need to know what exactly is happening in the microstructure of that steel, so that we can get something better and something higher than what we've gotten before. So I will just say that, most importantly, I'll just say that it has the ductility, which we know. We know we know what we mean by ductility. Ductility, ability to elongate, ability to stretch. And that is just what we need in every panel of any transport system, and even in construction system. So, like I said here, the basic advantage is that the good morphological constituent, the fine grain. Of course, when you heat it up, there's always this crystal movement that makes it to settle. We have a fine grain of the steel, which we have with. The number two says it has a good equilibrium of modulus elasticity. Of course, the yield strength is very low. And when you have a low yield stress, means it's just what you need for any system. Vis-a-vis Gabella. I'm sure we're going to work with them. And so it has good structural stability, both at room and elevated temperature. So what do we need? Well, we need something that can withstand all weathers. We need something that can stand all pressures. Then I said proper solution to problem experienced in transport industry in terms of material failure. So these are some of the things. Time will not permit me.
You need to conclude.
Oh yeah. So these are the train wheel parts in which this dwarf steel. These are the on the frame. It's useful in the underframe, in the subframe, the main frame, some major parts and the panels. Yeah, some guys have done this before, and on bitumen they have done this before. These are the few guys that have done this, but we have gone beyond this. They started with bitumen at 100 degrees centigrade, but we are taking our own quenching medium, which is bitumen, at 230 degrees. So what do I mean by that in the methodology? And I'm going to round up and close from here. We are going to heat up the bitumen at a controlled temperature of 230 degrees. Somebody's going to ask me that, why are we eating up a quenchant? Because that is what is going to give us what we need by what we have researched so far. So we're going to heat it up to 230 degrees, and then after heating up this substrate, this material, this same salt, dwarf steel, the DP steel, we're going to quench it inside the bitumen of 230 degrees. Then we're going to allow it to cool, meaning tempering.
Moderator.
I'm not sure he has the right to what's going on here? Is that politics here?
No, your time has been up.
So,
What just happened?
so I just said the problem statement, like I said, I've said it in this, the careful alteration of processing parameter has not been taken into consideration before, and then we don't have a better mechanical. Then these are the processes which I just told us now. I've said all of these ones. I've said this one, and then this is just what I'm just telling you that we have to eat it up.
Your results then.
Yes, and then I said that, and the solution. This is the solution to it at the end of the day. We have an improved tensile strength and ductility, adverse impact, resistance, wear resistance, and lightweight, which is most what we actually need for every auto transport facilities. So it's a where are this, what are the potential benefits and relevance to the industry? Yeah, they are used on the train wheel parts, the train, sub-train, on the frame, and the main frame and the subframe. Yeah, we want to thank these guys, TUT and the rest of them. Thank you for making it a reality to be here. And then these are references, and thank you. Question?
Thank you.
We are quenching in bitumen.
Yeah, with 100.
The viscosity level of bitumen will not allow you to quench even below 100 degrees. If you know, maybe just go and do your research when you get home. Now we are doing 230, meaning that it's now elevated beyond the threshold, which is the lowest. So, and we are getting our result. We are going to get a result for that. But maybe in an advanced, maybe when we advanced, and after this one, because by, I'm sure in the next 3, 4, 5 months, 6 months, we should be done with the report. Then we'll be able to tell you that, yeah, this works. But we want to go, like I said, the research. We're going to go beyond that. Maybe when we make it to 50 now, something else will happen. That's why it's a research. It's an ongoing thing.